Hello, this is Wyatt Stute presenting the Impeller project for our group. Our group is Andres Gonzalez, Logan Power, Devin Judice, Wyatt Stute, and Cameron Christie. And our group had for manufacturing process MCHE 365, we have the Impeller project. So a quick introduction to the project. We have a few design criteria that we were given. We have to achieve at least a 50 psi gradient across our pump. We have to have a minimum flow rate of at least 100 gallons per minute. We have to have a maximum rotational speed of our pump of 4,000 RPMs. We're going to idealize our pump to have an efficiency of 100%, all while minimizing weight as well as cost. And we have a few design constraints that we have applied to our projects. So we can only have up to 8 vanes in our pump, so we can have 8 of those fins. Our inlet diameter is a minimum of 3/4 of an inch, so that's a minimum. A maximum height of 2 inches, as well as a maximum diameter of the entire part of 4 inches. And that maximum height and diameter are after post-processing, so the cast can be larger as long as the post-processing product is under those constraints. All of this will also be balanced against cost, and we will be considering other things as well, such as our material selection and our design for manufacturing and assembly. More of our introduction is our scope of work. So our team decided that we'd have to make a CAD model and part ID, so that way we could be able to print our pattern. We have to select an alloy using Granta EDU pack. Although this was not available for us for this semester, this was the goal of the project, so we were not actually able to do this since Dr. Rausch was unable to provide Granta. We had to design a mold system for directional solidification using the Russian guy's rule, Shiranov's. We also had to try to balance out our design to allow for to set some optimal casting parameters to be able to figure out the best way to design it so that way it will be most easily cast, as well as cast and removable from the mold so that way it would be strong. So we have a few things to consider with that, as well as like the speed at which it will cool to allow for our grain growth to help describe some of our because our manufacturing process will affect our grains, which will affect our properties, all of our mechanical properties. And of course, through this whole thing, we're applying DFMA principles to reduce post-processing, although with our part, we were not able to completely remove all post-processing processes.
All right, I'm Cameron. I'm here to talk about the background. The parameters that will influence our castability include pump performance, inlet size, solidification control, which will prevent shrinkage defects, design constraints that include mechanical load, our envelope, printer volume, castability index, and surface temperature. Theoretical calculations will include the blade width, the torque, mechanical power, hydraulic head, and the pressure. Alright, this is our material selection. We chose aluminum A356 because of its high yield strength, its density, its mechanical temperature, and its low cost.
This is Devin. I'll be going over the theoretical calculations that we had to use before we designed our pattern. So for equation 1, that was the vertical height of the blade. This was one of the two major things we had to factor in. It was majorly affected by both the flow rate that we would assume and the bottom radius of the entire part. And the number 1 shows the equation we used. It doesn't show all of the conversion factors, but it also gives us our number. For number 2, the torque is part of our what we need to solve for. We need to reach an ideal certain pressure. To solve for the pressure, we needed to first get the torque, which is shown in equation 2. Once again, this does not show our conversions we had to use, but that led into our mechanical power that we would achieve, which was needed to solve for hydraulic head, which could then be turned into pressure as shown in number 5. The goal was to reach 100% efficiency, which would be considered at 50 psi of pressure increase. We were able to theoretically get 65 psi, which would be over 100% efficiency. The way we had to, some of the major considerations was obviously our flow rate and our bottom radius. These majorly affected everything from step down. Besides the vertical height, that was fairly independent of everything else, but it did majorly affect the torque, which would majorly affect our pressure.
This is Logan Power, and I'm talking about the methods. The CAD design process was done in SolidWorks. It took a couple attempts to build the part along with multiple tutorial videos. After building the pattern, a makeshift sprue was created in a ring shape to glue on the outer diameter to the bottom of the pattern. This helped us lift the pattern out of the sand. To cast the part, paraffin wax was used as a substitute to our material, which was aluminum A356. Kinetic sand was used as a replacement of green sand. The green sand was hard to find to purchase. A cake pan was used to hold this kinetic sand into one area. We put the pattern at the bottom of the cake pan and filled it with the kinetic sand. Once packed tightly, the pan was flipped over, and the ring that was glued to the bottom of the pattern was now on top, which allowed us to pull out the pattern without disrupting the sand too much. The wax was then melted using a hot plate and poured into the cavity where the pattern was. After solidifying, the pattern was removed. This is the CAD design of our impeller. Our inlet diameter chosen was 1 inch. Our outside diameter was 4 inches, which was the maximum. Our height was 1.63 inches. The amount of vanes we used was the maximum, which was 8. And the blade vertical height was 0.255 inches as previously calculated.
This is the supplies and cost sheet that we made. As you can see, we listed out everything we needed to purchase and the prices. It shows down below that the hot plate that we used was $0. That's because it was provided to us in the lab on the first floor of Ruja.
This is Andres Gonzalez. So here's the final product we got from our casting. If you look at the bottom view, you'll see a white plastic ring. We glued that to the wax pattern to help us pull it out of the kinetic sand mold. That ring really helped avoiding damaging the shape, but even with that, the wax stuck onto the sand and a few fins broke off when removing it. Also, some of the fins had a slight wiggle to them and they were thin and fragile, which made casting harder. In the future, we'd probably tweak the design for better castability, like thickening the fins or adjusting their geometry a bit. Here you can see a side-by-side comparison of the wax pattern and the final product. Most of the main geometry came out pretty close to the CAD model, especially from the top and side views. But notice the extra material on the back, that's from the sprue, which was designed to fit in more wax as the part cooled and shrank. It worked as planned, helping the part fill properly, but now we have to face off that extra material as a post-processing step to get a flat, clean surface. And that wraps up our final product and what we learned from the casting process during this project. Thank you.